It's very common to run a statistical experiment where what we're doing is counting up successes and failures on repeated binary trials. So if we're thinking about running the same binary experiment over and over and over again, each time we either get a success or a failure, we might just want to know, in total, how many successes did we get? And when we're running an experiment that takes on this form, this is going to be characterized by the binomial distribution. So if a random variable counts the number of successes in a fixed number of trials, each of those trials being binary, then it's said to follow the binomial distribution. So what does the binomial distribution look like? Well, x is going to be a random variable that takes on values between 0 and n. N is some positive integer. Then x here is obtained by counting the number of successes on repeated Bernoulli trials. A Bernoulli trial is going to be a single binary statistical experiment. So we can think about flipping a coin, for instance. We either get a heads or a tails, a success or a failure. And maybe what we want to do is we want to count how many times did we have successes? How many heads did we see if we flip the coin 10 times? The number of trials is going to be fixed at some constant, and in particular, it's going to be fixed at the constant n. So we know how many times we're performing the experiment before we start performing the experiment. The distribution of x in this case is then referred to as the binomial distribution. We say that x is a binomial random variable, and the two parameters that we care about here is going to be the number of trials, which we call n, and the success probability of every trial, which we call p, right? So the number of trials is n, the success probability is p. If you know how many trials are you running and what is the probability of success on each of those trials, then you know everything you need to know about the binomial distribution. Now, once you know that something is a binomial distribution, we know what the probability mass function is, and specifically in this case, right, we say that x follows a binomial NP distribution. Okay, the tilde here means that that's the distribution that it's following, right? N and p are our two parameters. And then the probability that x takes on any particular value, right, between 0 and n, is going to be given to us by n choose x. Okay, so this is using the combinations here, times by the success probability to the power of x, times by 1 minus the success probability to the power of n minus x. Okay, so this is the probability that x takes on any particular value. Now, if we want the summaries of these, the expected value is going to be n times p, and the variance is going to be n times p times 1 minus p. Okay, and so then if you know that x is a binomial, you know, well, what's the probability mass function of x? You know the expected value, and you know the variance of x. So, taking the standard example is always going to be coin flips, right? A fair coin is flipped 10 times. X is going to count up how many heads we actually observe. So what is the distribution of x? Well, every time we flip the coin, we either get a heads or not. That's a success or a failure. Okay? We're repeating this a known number of times. So there are 10 times that we repeat this experiment. And as a result, this is going to be a binomial distribution, right? In terms of the parameters, we know that there are 10 trials being performed, so n is equal to 10. The probability of success on any given trial is going to be 0.5 because it's a fair coin, right? So this is binomial with n equals 10 and probability of success being 0.5. What's the probability that x is equal to 3? Well, here we can plug into our probability mass function, right? So the probability that x is equal to 3 is going to be n choose x, so that's 10 choose 3, times by the probability of success, which is 0.5 to the power of x, times by 1 minus 0.5 to the power of 10 minus x. Okay, and using this formula here, right, that comes directly from our probability mass function, plugging that into our calculator is going to give us the actual probability there. Right, so the PMF with 3 plugged in is 10 choose 3 times 0.5 to the power of 3 times 1 minus 0.5 to the power of 10 minus 3, which gives us 0.11171875. Okay, so the probability that you roll or that you observe exactly 3 heads on 10 flips of the coin is about 11.7%. What's the expected value of x? Right, so the expected value for a binomial is always n times p, and so that should give us 10 times 0.5, right, which is 5. We expect to see 5 heads. What's the standard deviation? This is the square root of n times p times 1 minus p, the square root of our variance, right? The variance is n times p times 1 minus p. So that's 10 times 0.5 times 1 minus 0.5, which if we work that out, gives us 1.58114, right? So the standard deviation of 10 flips of a fair coin, counting the number of heads we get, is 1.581. Okay. As soon as we've identified that this is a binomial random variable, the probability mass function, the expected value, and the standard deviation or the variance all come for free. Let's take a look at another example here. A pair of fair dice are tossed 3 times. Okay. What's the probability of getting a total of 7 at least once? Okay, so let's think about this, right? We have x is going to be equal to a random variable, and what this is going to do is this is going to count the number of times that we get 7 on pair of dice, right? And we're tossing this 3 times, so we know n is going to be 3, right? In terms of the probability, well, the probability that we are going to roll a 7 is actually going to be 1 in 6, right? How can we figure this out? Well, we know that there are a total of 36 possible rolls on the dice, right? If you roll 2 dice, there are 36 total outcomes, and 6 of those, right, are going to equal 7. And that's if you roll a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, or a 6 and a 1. So there are a total of 6 of those. So 6 out of 36, which is 1 in 6. Okay. And so then what we know here is x is going to be binomial with n equaling 3 and p equaling 1 over 6. Okay. And so what do we want here? Well, we want to know, well, what's the probability that we get a total of a 7 at least once? And so that's the probability that x is greater than or equal to 1, right? We can either write this out as the probability that x is 1 plus the probability that it's 2 plus the probability that it is 3, or we can say, well, that's 1 minus the probability that x is 0, right? The probability that x is 0 here, right? We can get this using our probability mass function, right? So we're going to take n choose 0, so that's 3 choose 0, times p, which is 1 over 6, to the probability, or to the value of x, which is 0, 1 minus 1 over 6 to 3 minus 0. Right, so we plug this in, 1 minus that gives us the probability that we're looking for here. So again, by noticing that this is really a binomial random variable in hiding, we can work this out fairly straightforwardly. So this is binomial with n equals 3 trials. The success probability is the probability of rolling a 7, which is 1 over 6. So therefore, x is binomial with n is 3, p is 1 over 6. We want the probability that x is greater than or equal to 1, which is 1 minus the probability that x is 0. Using the binomial PEMF, we plug in 0 into that equation, right? That gives us 125 over 216, which tells us that the probability of the complement is 1 minus 125 over 216, which we could have as 91 over 216, or about 42%, right? So the probability of getting a 7 at least once is about 42%. Now, find the probability of getting a total of 7 exactly once, right? Well, here what we want is just the probability that x is equal to 1. Right? That's exactly what we want, which, in our case, we already know the distribution of x is binomial, and so that's just p of x of 1, px of 1, so that's 3 choose 1 times by the probability here is 1 over 6 to the power of 1, 1 minus 1 over 6 to the power of 3 minus 1. Right? So all of this becomes easy to do because we've identified x as being binomial up here. Okay. So working through that expression here, we plug in 3 choose 1 times 1 over 6 to the power of 1 times 1 minus 1 over 6 to the power of 3 minus 1, which gives us 25 out of 72, or about 34.72%. Okay. So there's a 42% chance, roughly, that you get 7 at least once, and a 34.7% chance that you get 7 exactly once. The binomial distribution counts the number of successes when you have a fixed number of binary trials. Right? This comes up a whole lot of times. The standard example is thinking about counting how many heads show up on some fixed number of tosses of a coin. Once you know that this is the pattern that you're following, what we care about is how many trials are there, what is the success probability. Once you know those two parameters, you know the PMF, you know the expected value, you know the variance, and calculations with these quantities become a lot easier to work with.